Hey all, welcome to this video on AP Statistics. It's the first one that I've done this year, so hopefully it'll be helpful and hopefully you'll enjoy it since I'm not in class today. To get started, what we're going to talk about with sample proportions and the distribution of sample proportions from some sort of sampling is let's do an example that I think will help us to understand what it is. So for this video, let's consider a Costco-sized bag of Reese's Pieces with 1,000 pieces in it, so genuinely Costco-sized, pretty big. And let's say that we're told that 40% of the pieces are orange, and we're going to select samples of 50 pieces, so like the biggest handful you could get, I would imagine. And we're going to say that X is the proportion of orange candies in a sample. So first thing to understand is what is a proportion? Okay, because like when we talk about proportions, for example, in algebra class, we're talking about all kinds of fractions set equal to each other, things like that. A proportion here, all it's saying is like what percentage of the candies that you grab will be orange. So maybe you come out and 52% of the ones you picked were orange, so your sample proportion is 0.52. That's all it's saying, which is a little different than the mean. The mean would be like, what's the average number that you draw? So maybe out of 50 on average, you get 20 or something like that. So versus our proportion, it's going to be less than 1, right? Because 1 would be 100%. So first of all, let's do a quick review. What type of probability distribution are we looking at here? Are we looking at a normal, a binomial, a geometric, a skewed, a bimodal, something that's uniform maybe? Let's see, think about that for just a second. Okay, well, it turns out this is a binomial. The reason for that, look at it. We know the number of trials, or the number of, essentially each of the 50 pieces is its own trial. Okay, so we know that, and we know the probability of success, defining success as being orange for any one of those. So we actually know this is binomial. Okay. And then we have an applet right here. So if you want to go into the OneNote, this is in your OneNote. You can click on this link right here and pull up the applet so that if you want to play around with what we're going to do, that would be fine too. All right, so guys, I've made a couple of changes here. I've changed from orange to proportion. Number would be like if we're talking about the mean. I've changed it to proportion. We're going to do one sample on this first one. I've said that we're selecting 50 candies, and I had to change this from 0.5 to 0.4 to match our scenario. So let's take our sample and let's see what we get. All right. Hey, look at that. It actually landed right on. I'm surprised. That's really unusual. Let's do another sample and see if it happens again, because that's actually really surprising that it landed right on the expectation there. Okay, so here, this one's 0.36. So notice it's going to graph these as we go down here. So I'm going to keep drawing samples. I'm going to go ahead and just toss like 50 more samples on here so we can start to generate some data. And we'll see how long this takes. Hopefully it doesn't take too long. There we go. All right, so it's given us all these data. All right, so we're starting to see the proportion. I'm going to include the summary stats because that's what we're going to be working on in this lesson. So they give us our mean and our standard deviation. I think I'm going to just throw a bunch more, like maybe 500 more data points on here just so we can see. And it's going to take a minute to do that. And notice these summary stats, the mean and standard deviation, are going to update when this pops up. All right, so we're at 0.402. And we've got some sort of, it's kind of approximately normal, and 0.070 on here for our standard deviation. So with that, we can kind of see now the distribution of proportions. It looks like our maximum we had out here was like 0.62 or 0.63. So even though only 40% of the actual candies are orange, in some of the samples, you get a pretty high proportion, and down here it looks like we have maybe 0.19 or something like that. So that's even less than half of what was expected, but we know that anytime you do a bunch of samples, you can get some really extreme values. All right, now there are three key features of the sampling distribution of a sample proportion. Okay, we are calling that p hat because that's what it's typically referred to. And here they are. Now I've put these in a box. These are kind of like the big things you need to get out of today's lesson. The good news for us is that these first two equations are included in the formula sheet that we'll have for our AP exam. So we don't have to memorize them, but we do need to understand what they mean and how to use them. So that's what I want to talk with you about now. So the mean of our sampling distribution is going to be P. So all that's saying is if we take enough samples, the average of all those samples should come out to be the actual. How does that compare to what we saw a minute ago? We saw that our sample mean, or our average of sample means, So our mu sub p hat was 0.402. Okay, and we knew the actual mean was 0.4 because that's how we define the question, that the sample proportion, excuse me, that, and I should be putting p for that. The actual proportion was 0.4. So all this is saying is, if we did all the possible trials, all the possible iterations, this would eventually come out to be 0.4. So how would we phrase that in common English? So if we average p hat, so the sample proportion, for all samples, we get the true proportion. Okay, and this is our true proportion here because that's what we were told. Now, what does that tell you? If you have some sort of a statistic, and this is a statistic, okay, and this is the parameter, so I'm going to put a little s here for statistic, p is for parameter. Okay, if we have some statistic and the average of all of the possibilities for that statistic average out to be the true proportion, what do we say about that? That tells us that p hat is an unbiased estimator. All right, and that's good. What about the second one? We also have a way of finding the standard deviation of the sampling distribution, and they give us a nice little formula here. There's a condition, though. It has to meet the 10% condition, which is this right here. And so that's what I'm going to put into common English. Notice n appears twice. One is lowercase, and n is uppercase. So remember, n for this is going to be sample size. And capital N is the number of elements in the population. Okay, and so I'm actually going to write a sentence about that. I'm not going to make you watch me write out sentences on a touchpad for a computer on a video. That sounds really boring. I'm going to leave it like this. Okay, so guys, think about it like this. If, let's say that, how many candies did we have in the bag? So we had 1,000 candies in the bag. And so for us, capital N equals 1,000 for this example. And so we have to make sure that whatever, in order for this to apply, our sample size has to be less than 10% of that. So that tells us that N has to be less than 0.1 times 1,000, or N has to be less than 100. Okay, and so the setup we had satisfies that. We had chosen N to be 50. Okay, and so that's totally fine. Okay, what about the last one? And this last one is the one that's going to allow us to do some cool things, okay? We're going to say that the sampling distribution of p hat, that's the sample proportions, is approximately normal, approximately, as long as the large counts condition is satisfied. All right, guys, this is probably new to us, okay? Large count condition is satisfied. And so what they're going to say, that condition is as long as n times p is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. So let's try it. All right, we're going to find the mean proportion, and then we're going to talk about the true mean. The mean proportion, we had that from a minute ago. That was actually calculated from our applet. Let's go back to the applet for just a second. Okay, we have right here for what we did, the mean was recorded at 0.402. That was the mean of all of these sample proportions, all the p hats, okay, because each of these data points represents one of the values of p hat. So that was our sample mean. So this is 0.402. The true mean, okay, so I'm going to call that mu sub p hat. And then actual, no, I did it again. So actual p is 0.4, because that's what we were told in the beginning. Okay, so we kind of already discussed that up here. Okay, now why don't they match? Because we don't have every different unique sample of 50. If we had every single possible sample, that's what we're talking about when we say the sampling distribution of p hat. Okay, what about the standard deviation of our sampling distribution? Let's try that. Okay, this would be one that you might try to set up on your own right now as I give you a little bit of a pause in the video here. See if you can set this up on your own. Okay, one thing I noticed, because we're using this formula right here, and we already talked about the fact that we've met the 10% condition right here. So we demonstrated that. So yes, this does apply. All we need to know is what is P and what is N. Okay, so we know from the original question that P is 0.4, 40% of the candies are orange, and N was our sample size, so that was 50. So all we have to do now is plug that into this little equation. So sigma sub P hat equals P, so 0.4 times 1 minus P, we're going to do mental math on that, that's 0.6, and then we're going to divide that, oops, if I didn't drop my square root down far enough, so divide that by 50, and let's type that in a calculator. Let's see what we get. I'm going to type it along with you here. Okay, and I get 0.069 when I do that. What about this last one? Are we able to say that the sampling distribution is approximately normal? Or the sample distribution of the proportion is approximately normal? Okay, let's see. We'll run it through this condition number 3. We're able to say that it is, as long as the large counts condition is satisfied, namely, n times p is greater than or equal to 10. Okay, let's try that. So, np greater than or equal to 10. What is n and p? So n was 50, that was our sample size. P is our sample proportion, so 0.4. 0.4 times 50 is 20, which is greater than 10, so that works. We also have to check the second part of it. Okay, so n times 1 minus p, so that would be 50. 1 minus p is 0.6. Y'all, I can already see that 50 times 0.6 is going to be a bigger number than 50 times 0.4, so I'm not even going to bother to keep going, because that clearly is going to be larger than 10. So what is our answer? Our answer is yes, and we've demonstrated so right here using the large counts condition. All right, now let's try a little bit more interesting question. Okay, let's say that the true proportion of orange in the bag is 0.4, 40%. We're going to select that same simple random sample of 50, but we're only going to do it one time now instead of doing 1,000 trials to understand the distribution. We want to know what's the probability that we're going to get 45% or more orange for that sample. That's what this is saying right here. It's your sample proportion, meaning what's the probability that we get more than 45% or 45% or more orange for that sample. Okay, so there's a couple ways we can start to think about this and access this question. Importantly, in the previous question, we said, yeah, this thing is approximately normal, so let's think of it as being approximately normal, which means we could apply the normal curve. Now, we would need to know the mean to do a normal curve, and so we actually showed that previously as well. We showed that right up here at the top of the screen. Okay, right here where we knew the population was 0.4, and because of this first rule, the mean of the sample proportions is the actual proportion. So if the proportion is truly 0.4, which in this we're being told it is, so we're going to go with that, that would tell us that right here, this mean is 0.4. So now I'm going to annotate it as mu sub p hat, and that's 0.4. Now in this question, we're asked, what's the probability that's going to be greater than 0.45? So that's just this. So when we go to do our normal distribution calculation, let's actually pull up the Inspire here. So I'm going to go normal distribution, so menu 55, and I'm going to go to normal CDF. My lower bound is 0.45. My upper bound is going on forever, as we saw in the image. The mean, we're told, is 0.4, and the standard deviation we calculated 2 questions ago at 0.069. Let's see what we get. 0.234. All right, so 0.234. Let's pause and ask ourselves if that makes sense. Does it make sense to you that this shaded region would have an area under the curve of 0.234? Yeah, absolutely. If it was from 0.4 to the right, it would be 50%. We're missing this chunk in the middle here, so 23.4% is pretty reasonable. That's our main ideas for the day. So let's take a minute now and let's see how much that made sense to you, how much you understood. We've got 5 questions here, all with one context. Guys, what I want you to do here, please pause the video and try the whole thing. Then I'm going to walk through each of them and we'll be done for the day. So pause now, please. All right, we're supposing that 3 out of 4 young adult internet users watch online videos. We have a polling organization that's going to contact an SRS. Guys, you figure out what that means? That's simple random sample of 1,000 young adult internet users, and they find that the proportion p hat in the sample who watch online videos. All right, what's the mean of the sampling distribution? All right, we were told earlier that the mean of the sampling distribution was p, which we're told in this question right here is 0.75. All right, that one's easy. Calculate and interpret the standard deviation of the sampling distribution. All right, so that's the one where we have p times 1 minus p over n with the square root. Let's do this. Should be pretty easy. That's 0.75 times 0.25 over, what was n for us? That was 1,000 here. All right, let's type that in, see what we get. I'm going to round mine off here to 0.014. Now, y'all, if you rounded this a little bit differently than me, which, I mean, you would have kept more digits. Please don't keep fewer digits than this. But if you kept more digits, that's fine. It will throw off these answers here at the end, so that's okay. But just be ready for that. And then we have to decide, is the sampling distribution approximately normal? We're going to check the large counts condition. All right, the large counts condition is the one that says your sample size better be less than 10% of the population. So our sample size was 1,000, which seems really big, but we have to ask, is that less than 10% of the number of young adult internet users? So do we think that there's more than 10,000 young adult internet users? Yeah, in the state of Washington, there's probably more than that. So I'm going to say in general, that's definitely true. So I don't know what that number is, but I know it's way big enough to satisfy the 10% or the large counts condition. So we get to say yes, which brings us to the next one. Find the probability that a random sample will give a result within 2 percentage points of the true value. All right, we just said it's normally distributed. So let's get our normal distribution. We know that the middle is at 0.75, so 2 percentage points on either side would give us 0.77 and 0.73. Notice we already found the mean in part 1, and we already found the standard deviation in part 2. There it is, standard deviation and mean of p hat. So we actually have all the information we need to go type this in a normal CDF. Okay, so type that in. When you do, you should get something in the neighborhood of 0.847. Now, y'all, you're going to find that if this number was a little bit different than mine because of rounding, your answer here is going to be way different. Okay, now I'm not super freaked out about that if you got the concept down, at least not for today, but something you want to be aware of. This one needs to be exact. Okay, they gave us 75%. You need to have exactly 0.75 there. So what's the probability that our sample will yield a proportion within 2 percentage points of the true value? Pretty darn likely. Yeah, almost 85%. And then, if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution? Okay, here's how we think about this. 9,000 is 9 times bigger than 1,000. So what would have happened right here with our standard deviation? We would have had the same old thing, 0.75 and 0.25, and I'm going to put 1,000 here with a 9 next to it just to demonstrate that it's times 9. And the reason I do it this way is because we know how to take a square root of 9. So this is equivalent to 1/3 of that same thing. So square root of 0.75 times 0.25 over 1,000. So what does that tell us? That tells us that the standard deviation decreases to 1/3. To 1/3 of what it was. Okay, and then what about the mean? They're really asking about the mean here. Does the mean change when you take a bigger sample size? No. No, it would be less variable, which is what we're showing here, but the mean proportion would be the same. So I'm going to add that in here. Mu sub p hat is unchanged. All right, y'all. So that's it for today. Hope the video was helpful and you enjoyed it. I'll see you next time back in class. Assignment time, go.